Okay, so uh, we have seen the calculation of the VTH. So we'll see again, we'll come back to this equation again. So what is observed, so if I try to plot this threshold voltage with respect to Kr, right? So with respect to Kr, so this is what it is seen. So there is some typical value for this process. So this is a VDD with 3.3 volt with the threshold voltage of VTN again 0.6, and the threshold voltage of the PMOS device, of course the magnitude is 7 volt, 0.7 volt is this is the absolute value, 0.7. So it is seen that whenever this Kr, which is Kn by Kp, if this is varies, this VTH values will vary like that. So depending upon where is my this value, what is this my value, this Kr, which is the ratio of Kn by Kp, it will vary. So whenever this Kn by Kp is is little large, if this ratio, is very small, smaller than the 1, then smaller than 0.5, then it will go towards VDD. So this is towards VDD, right? This is towards VDD, this is towards ground. So it will go towards VDD, and as the ratio becomes higher, so the the this threshold voltage will come down. So why it is happening will come again. Will come again in the next slide. Why this is happening? The reason for this is we'll come to this point a little later. So again, I think yeah. Here again, a little bit shifting back to the topic, to a little different. So you can see this VTC curve here, right? We can see this VTC curve here, and of course the if you see observe the current, the drain current will be something like this, right? So you can see here when the output, okay, whenever the input is very small, of course at this time the output is high VDD, and whenever the input is very large and the output is small, we can see that there is no current, static current. However, in this transition state, we can see that there is this there is this change in the peak current. So you can do this kind of again you can do this kind of simulation in LT-Spice. So just like I have shown last time in the LT-Spice, here also you can do like I already have made this this one CMOS inverter. So again I'll share even the LT-Spice file also. If you see in the website, you will see that I have shared last time's this LT-Spice files. So you see I have this CMOS inverter, right? So I have this NMOS here and the PMOS here. The body is connected to VDD for PMOS. The body is connected to again the ground to for the NMOS. I have the supply voltage which is 1.2, and again I am using this 65 nanometer files. And currently I am trying to sweep this voltage, right? Sweep this voltage from 0 to VDD, which is 1.2, and I am trying to observe the VTC. So if I have done all this setup here. So if I run the simulation, right, and try to plot this V out, if I just try to plot V out here, so you can see here this is my graph. So you can see here there's a sharp transition, right? Sharp transition which is starting from VDD, and again it's going down to 1.2 volt, right? It's going to 1.2 volt VDD as I'm slowly increasing. So here I have adjusted my W by L such that the the threshold voltage of this inverter is very close to VDD by 2, because VDD by 2 is 0.6. So you can see here this is very close to this VDD by 2. Now we can plot the current also. So if I try to plot this current, so if I go here and if I just try to go if I just hover around, and my cursor will change to something like this whenever I come to this point where I'm trying to plot the current through the NMOS device. So if I just plot this current, and if I go back to my this one, if I click it, so you can see that, you see this is current, right? So whenever the MOS is in trend, and this kind of region, you can see that a current of around 200, close to 240 microampere will flow. So whenever my doing this transition, of course these are all static behavior, this is not dynamic behavior, of course. So the dynamic behavior, the dynamic currents, that will come eventually. So you can see here that as the transistor goes from this as the output goes from VDD to ground, so there will be a region, in this mid region we can see that there is a high current. So you can try out yourself. I'll be sharing this LTSpice file again, so you can try out and do your own simulation like that. Okay, so so coming back, so you can see this, you can get this similar kind of course this value of this current and all will be different, because the technology used by this book is different, and the technology that I am using is different, because it is going for around VDD as 5 volt. So the drain current and all will be this magnitude will be different, but you can see that the characteristics and the behavior of the circuit and the profile are all similar like that. Now design for the design of an inverter, like coming back to this point of the threshold voltage, like the as I have mentioned that the inverter threshold, the threshold where this V in is equal to V out, is one of the important parameter in CMOS device. As I have mentioned, because of the full swing nature, because the output is going from VDD to 0, because this VOH is VDD and VOL is ground, so the noise margin of an inverter is quite good. So the designer doesn't much focus and on the noise margin. Of course, we also have not much control on the noise margin, but we don't have much hold on this noise margin. We cannot vary much, but what we have, this main point, what the designer sees is the setting the threshold voltage. So trying to threshold voltage, a good inverter tries to has an inverter threshold voltage which is VDD by 2. So trying to set this threshold voltage to VDD by 2 is a good design basically, because if you see when it is VDD by 2, right, half of my beyond half VDD by 2, there is this level of my logic 0, and below VDD by 2 I have this region of logic 1 in terms of output. So that's why the main target of a good design, the main target of a good CMOS inverter is trying to set this threshold voltage to VDD by 2. So if you go back to this equation, and if we try to a little bit rearrange this equation, what I will get is again I will get this kind of expression, right? So basically what we are trying to do is trying to set a proper value of VDD by 2 VTH, such that I get this VTH as VDD by 2. So we'll see how do we set these parameters of the CMOS inverter such that my VTH is VDD by 2 or close around VDD by 2. It may not be exactly VDD by 2, but it's very close to VDD by 2. So if I rearrange that equation, I'll get this kind of, again, not that this is not the magnitude, this is the absolute value. So solving for Kr, if I just rearrange this equation, if I just square it and then rearrange my equation, Kr equal to, which is Kn by Kp, I'll get this kind of expression. And finally, if I solve it, if I solve this one, what I will get is Kn by Kp of an ideal inverter, and I want this threshold voltage, right? I want this threshold voltage to be VDD by 2, right? 0.5 VDD, because for an ideal inverter, VTH is VDD by 2. So I want this VTH, the point where my V in equal to V out should be equal to VDD by 2. So if I try to rearrange this equation, what I'll get is I'll get this kind of expression. Of course, again, I am doing this little modification here. So this should be the mod. Of course, different people use different ways of notation. This way to write this way is also right. I'm not blaming that, but my point is, like, if you try to write the absolute value, things becomes very easy, simpler like that. So so if you can see here right now, the 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 Kn by Kp should be equal to this one. So if I satisfy this condition, then I will get my VTH VDD by 2. Now in this case, if you see this one, if the threshold voltage of the PMOS and the NMOS are same, then this whole expression here, it will become turned to 1. So which is not true, because it is not necessary that these two will be equal, but assuming that they are equal, or they may be very close, right? So they may be very close, they will definitely not be equal, there may be little difference, but if we considering them to be very close, then what we'll get is Kn by Kp for a symmetric inverter is equal to 1. So let's assume, for time being, let's assume that the threshold voltage of both the inverter and both the NMOS and the PMOS are same. But of course this is not same, but we can approximate to be 1 like that. So now again, what are this Kn by Kp? As we have mentioned, the Kn by Kp is mu n Cox W by L. This is N, and mu P Cox W by L is P is equal to 1. Now because this both NMOS and PMOS are fabricated on the same wafer and the same process, and the fabrication process of the Cox, which is basically the depends on the oxide thickness, is same. So these two are almost basically same, because they are fabricated on the same in the same step of the CMOS fabrication process, as we have discussed in our, I think, second or third class. So we can cancel out these 2 points. So what basically I have now will be, if I just rearrange this equation, right, W by L of N and W by L of P will be equal to, if I take this mu P up here, mu P, and if I take this mu N down, get mu N down. So what basically I have finally come out to get an ideal inverter characteristic is my W by L ratio of the NMOS and W by L ratio of the PMOS should be the ratio mu P by mu N. So what is again the mu P? Mu P is the mobility of the holes, and mu N is the mobility of the electrons. So finally what I have got is the ratio of W by L of N and P should be like that, will be the mobility of the holes and mobility of the electrons. So we know that from the semiconductor physics, the mobility of the electrons is, mobility of the electrons is higher than the mobility of the holes, right? So what is the mobility of the holes? So mobility of the holes is I think is whenever there is absence of electrons, right? So basically from semiconductor physics we know that this mobility of the holes is much smaller than the mobility of the electrons. The electrons are more mobile than the holes. That's why if you see this ratio, what you'll get is, it depends of course on the fabrication and the doping concentration and different stuffs. So but what it is approximately, what you'll get is 1.25 times. So this will be 25 times higher than the mobility of the holes. So basically what we will have now here is, what I will have here now is the ratio of n. So the ratio of P. So what I will get is W by L of the PMOS device is approximately, not equal basically, is approximately 2.5 times the W by L of N. So this is my final, I should say, final conclusion. So of course this is not exactly 2.5, there will be a variation, because as I have mentioned here, we have assumed that the threshold voltage of the NMOS and PMOS is equal, but of course from this equation we know that they are not equal, they cannot be cancelled. So this ratio is not perfectly 1, but here we have just assumed that it's 1, and this is assumed so that it's a good starting point. So so I can say that the size of the PMOS should be more than twice the size of the NMOS. So this is a very important conclusion, because you know that the reason is the mobility of the holes is slower than the mobility of the electrons. So the thumb rule is the size of the PMOS should be around 2.5 times, but this ratio is not exactly 2.5 times. It can be higher, because as I've mentioned here, we are ignoring we are just approximating that their threshold voltages are equal, but it's a good starting point, especially when you are designing. We can start with this point, and then you can fine tune your W by L according to what is required to get the ideal inverter characteristics, which is VDD by 2. Any clarification on this? Any questions? Any questions? Is it clear? Hello? I hope it's clear, right?
Yes, yes, yes.
Okay.
Yes, sir.
Okay, great. Thank you. So we can see here, right? We can see here, like we can see here, depending upon what is my this ratio, right? What is my ratio, like depending upon where is my ratio, we can see the curve is getting shifted, right? So depending upon what is the ratio of the W by L ratio of the PMOS and the NMOS device, my whole this curve is getting shifted. So if I plot this V in versus V out here, the you know the so if I try to plot, if I try to plot this kind of this is the point where V in equal to V out. This is the point. This is the line where V in equal to V out. So we can see here, this case is not a very ideal case, because it I should say this in this case. So although this is this is not this is, of course, this mine line is not very perfect. So I should try to intersect this point where this is equal to this is equal to VDD by 2. So if I whenever I am designing, if I try to intersect this point at the VDD by 2, then then I have a good ideal characteristics inverted. I'll again show this point in the simulation, don't worry. So depending upon depending upon so depending upon where I am what I am fixing this ratio, my all this curve will vary like that. So this curve will vary like that. So let's again show it in the simulation. So in this case, of course, I have considered that this PMOS and DMOS, PMOS is here, it is around 2 micron, and here it is around 7 micron. So I should say that the PMOS is sorry is 3.5 times higher than 3.5 times higher than NMOS. So of course, as I have mentioned, although we have started the thumb rule of 2.5, but what happens, there will be a threshold voltage difference between these two, right? There will be a threshold voltage difference between these two, and because of which the value will not be exactly 2.5. Moreover, the mobility ratio may not be exactly 2.5. It depends upon the process parameters, different other process parameters like doping and other stuffs. So so that's why but roughly the thumb rule is around 2.5 like that. So if I want to suppose, if I want to do some kind of parametric sweep, if I want to see how it varies with the ratio, so let's vary my PMOS device. So let's write it as WP, right? Let's make it variable, and let's see at what value this this value becomes exactly equal to VDD by 2. So if I again, just like I've shown in the previous class, that if I use this step, so basically I'm changing this width of my PMOS. Maybe let's start with 2 micron, and let's go to 10 micron, right? I know the for this case to get VDD by 2 is around 7, so I'm going a little far beyond. So let's try to change it by how much? If I try to change by 1 micron step size, right? So, and just now you can again put it back here, and now you can just rerun the simulation. Of course, I don't want in this case the delete. So I don't want the case. I don't want to plot the current. So you can see this variation, right? As I'm going from as I'm varying this value, you can see that whenever this is 2 micron, it's something like this. But as I'm slowly increasing this value, you can see that this is varying. So I can see here at this point, the point where whenever this is at 6, right? Whenever this is at point 6, so I can basically try to find out this point whenever this is 0.6. So this will be the ideal value of my the ideal value of an good inverter. So we should try to set the value of the inverter at this point with VDD by 2, so that will be a good point. So you can see that depending upon the variation of the W by L, we can see that the whole curve is shifted from this point to this point. So this is the point where my WP is 2 micron, and whenever this is the point whenever my WP is 10 micron. So this is how you can, again I'll share this file so you can try out yourself. You can try out yourself and do different experimentation like that. Okay. So how do you understand this phenomenon that whenever for this case, why do that this curve shifts towards this lower value whenever I am whenever I am increasing the Kn by Kp ratio? How we can understand here is basically what happens is, um, in saturation region, uh, this is the whenever I am increasing my Kn, so for a smaller VGS I can get a higher current. So that's why this curve is shifting this direction, right? So for smaller V in, I am getting a same amount of current as the PMOS device, like that. That's why this is the reason. This I think say the reason to understand that why this curve is shifting like that, this side. So for this reason, like, because if my W by L ratio is higher, so for a smaller VGS, I can get the same current as the PMOS device, right? And for PMOS device, at this point, my because mm, of course, the VGS will be greater for PMOS device at this point. So, and because it has a smaller KP, that's why it gets adjusted like that. So, this is how we can understand intuitively why by increasing KR, which is also very clear from the equation, which is also very clear from this equation, But if we want to understand it intuitively, this is how we can understand.
Yes, sir.
Yes.
Can you please explain this once again? Like why the curve is shifting towards the left side when we increase KR?
Hello? Yes?
Hello.
Yes.
So I'm saying, can you please explain this once again, that why the curve is shifting towards the left side when we're increasing KR?
Okay. So what happens, you see, I have this, like I have, I have the PMOS and the NMOS device, right? So, so, so this current IP, right, due to the PMOS. So I am sorry, I'm messing up with the notations. So please bear with me. Yeah. So what happens is like now. So so if I am increasing this W by L ratio of this one, like I'm making it very high, right? So to get a particular current IN, I need a smaller VGS, right? Suppose I'm at this
Yes, sir.
point, everything is equal and all, everything is equal. I'm at this point, right? I'm at this point, so this current is equal to this current, like that. Now, suppose suddenly I have increased the W by L of this one, right? So what happens is, if I have increased this one, my VGS requirement will come down or not? Will come down definitely, right? So to get the same amount of current, to get the previous same amount of current, so definitely this curve will shift towards this side, right? Because this is my VGS. V in is the VGS requirement of this NMOS, right? Following? So to get the same current
Yes.
IP, right, to balance this point, right, I like that. I can say that my like VGS requirement will be smaller. That's why it will shift towards this side. Following?
Okay, sir.
Okay. Yeah. So this is very, I should say, very rough approximation, intuitive. So but of course, you can get more, more understanding better from the theory, but the equations. But this is how we can intuitively understand why this curve is shifting in this direction like that. So the opposite happens when you increase the W by L ratio of the PMOS. So the VGS requirement will be smaller. So this will shift towards this direction like that. Okay, so um, so so of course, the VIL and VIH for a symmetric. Just give me a moment. I'm just connecting my laptop to charger, so I get low battery. So next is suppose for an ideal inverter, like we have designed and like we have set the W by L ratio of the suppose we have designed a good inverter such that the VTH is VDD by 2, so close around VDD by 2. So with that condition, again we can resubstitute in the previous equations that we have got for this VIL and VIH. So if I resubstitute it, I'll get this kind of expression. So the expression will be very simplified. If you go back to, we have this expression for the VIL and VIH, right? So if I consider that the threshold voltage of the inverters are equal, and we have satisfied this, that we have made this Kr as equal to 1, right? And we have set the W by L ratio such that Kr is equal to 1. Then my VIL and VIH will be, come to this, will be something like that. So it's for a symmetric inverter. And finally we'll get a very nice conclusion here, that the summation of VIL and VIH is equal to VDD for case of a symmetric inverter, right? So VIL and VIH is VDD, which is very much clear from if you see this, if we go back here, which is also very much you can intuitively understand. Like suppose it is a symmetric, this point is at VDD by 2, I have this VIL and VIH. So what it is telling is that if I sum VIL and VIH, I'll get VDD. So which is very easy to understand, because if this is perfectly symmetric, the region from this point to this point will be equal to VIH to VDD, because it's symmetric, right? If we go this way, or if we go this way, they are symmetric. So the from this point to this point, they are equal because of the symmetric nature, right? So now suppose let's call it some value, maybe some x and x, right? So, and of course there will be this separation between these two. So let's call it maybe some delta x, which is the difference between the VIL and VIH. So this is delta x. So what I can write is, I can write VIL as, x, and VIH as x plus delta x. So now if I sum this VIL and VIH, what I will get is VIL plus VIH. I will get twice x plus delta x. So which is nothing but the VDD, right? X plus delta x plus x is equal to VDD. So this is how we can intuitively understand, even from this graph, that VIL plus VIH is equal to VDD whenever the my inverter characteristics is perfectly symmetric, like that. So I hope it's clear, right? Hello? There's no confusion on this, right? Okay, so then we'll proceed next. So that's why we have this VIL plus VIH equal to VDD. And so the noise margin can be calculated again based on the definition of the noise margin. Noise margin for the logic low is VIL minus VOL. So this is VIL itself, because the VOL is 0, and noise margin for the upper for the logic high is VOH minus VIH, and we know that VOH is VDD, so it's VDD minus VIH. So, and you can see here that again, as we have seen, if we just rearrange this, you will see that this n the noise margin at the lower side and the noise margin and at the higher logic side, they are all equal to VIL because of the symmetric nature, because we know that VIL plus VIH equal to VDD. So now what happens when we try to scale the power supply of the what happens when we try to scale the VDD power supply of the PMOS device? So for going for a low power design, when we have to go for a low power design, we have sometimes to scale down the VDD. So this is one of the technique of going for a low power design, which we'll see more in elaborately details in the later part when we'll be particularly focusing on the design, low power design. But just to mention in connection to the inverter, whenever my VDD is decreasing, of course we can go for a low power like we can go for low power operations, because we know that the power is very much dependent on VDD, right? So the expression of the power has this VDD term, right? So lower the VDD, the power is basically the total current drawn into the supply voltage, right? So whenever my supply for a given current, if my supply voltage is smaller, I can definitely get a lower power, lower power for the whole operation like that. So how do the inverter characteristics differ whenever I go for uh, low power? So we can see that the inverter characteristics still maintain its value, right? It still works whenever you are decreasing the supply voltage to a lower value. Of course, there is a limit. So the limit case is the VDD should not be less than the threshold voltage of the PMOS plus the threshold voltage of the NMOS. So NMOS and PMOS. So this is the, so it should not be less than, otherwise it won't be operating like that. So it cannot be, it should not be less. So this is the limiting case, but it can go to a very low value. So you can see here the VDD has gone from 5 volt to 2 volt. So there is a decrease in 2 volt, but still the inverter operation is maintained, right? The inverter operation is maintained. So you can see these various curves, but other thing happen. There's an hysteresis which comes into picture. So the hysteresis means the circuit has a memory whenever the VDD comes down. What it means is the inverter will follow these two parts whenever it goes from VDD to ground, whenever the output goes from VDD to ground, and whenever again it comes back from ground to VDD, it will follow these two parts. Like, so this phenomenon is called hysteresis, because the part or the voltage transfer characteristics is depending upon the logic state of the circuit. So whenever the output is going from VDD to ground, it is following this part. This part is defined by this arrow, right? And whenever the whenever the output is going from, or the input is going from high to low, and output is going from low to high, then it is following this path like that. So this operation is called the hysteresis operation. Again, this is also not very difficult to understand. This is why it's happening. So what happens is like whenever I'm slowly increasing my voltage, input voltage from zero. So you can see here my threshold voltage of the VT, this one has come to this point, right? Has come to this point, and whereas my the threshold voltage, right? Threshold voltage of the PMOS device, if I subtract it from VDD, so VDD minus the threshold voltage, it is at this point, right? So what happens whenever I am slowly increasing my V in, like slowly my increasing my V in. So the transistor is still in the cutoff region from this point to this point, right? From this to this. So it's not yet turned on, right? This point is turned on. So it's still at the VDD, still at the VDD. Now, as soon as it crosses this one, then it starts turning on. Then it goes to this point. Like that. It goes to this point like that. So that's why it will follow this path. Now, whenever it's going from the reverse, from when the input is going from VDD to 0, right? So for the MOSFET to this turn on, the MOSFET to turn on, it has to come all the way to this point. Otherwise, it will not satisfy it will be in cutoff region. It will not satisfy the threshold voltage requirement of the PMOS device. So, of course, the VGS should be greater than the threshold voltage of the PMOS device. Then only this will be turning on. So it has to come all the way to this point to for started switching like that. So this kind of hysteresis behavior comes up whenever there is the low power, when we are trying to scale down the VDD for low power. Of course, this is not a bad one. This is in fact good for noise, because it's whenever we have hysteresis, it has an ability, to have, it can sustain a noise like that. So it's not very bad. So this kind of little bit hysteresis is allowed like that. It's not a big issue. So I hope this is clear. Clear? No questions on this? Okay. So next, I'll just try to conclude for saying that the layout of the NMOS and PMOS, which we have a little bit last time discussed. So for a CMOS inverter, the layout looks something like that. So I have this PMOS here, right? I have this PMOS here. So this gate is here. So this gate can be connected to the NMOS, something like that. This is my NMOS. This is the point of my drain. This is my source of the NMOS device. Again, this is the contact for the drain of the PMOS. This is the contact for the drain of the source of the PMOS device, right? And this is the gate. So this is basically the gate of the NMOS device. So the gate can be connected to the polysilicon, and this is the output. So this is connected with basically metal 1, M1. So this is the polysilicon. So this is the metal by which these two drains of the NMOS are connected. So this is one way by which the inverter can be layout of the inverter can be done, and this is the other way by which we can rearrange this orientation such that these two gate can come like that in this vertical direction. So again, this is the gate, this is the drain of the, and this is the source of the PMOS device, and again this is the drain, and this is the source of the NMOS device, and this is the gate of the NMOS device. So they are sorted, and they can be the input can be connected here, and this is again the metal 1. This is the polysilicon. So where the input can be connected. So this is another type of another configuration for the layout of the CMOS inverter. Okay, so I'll end the class here if none of you have questions.